same thing. We're just assuming we don't have that special case. Okay, so let's assume that pattern they're at. You don't show a scale.
All right, let's take a peek at this. Number 4. And remember, I changed this to a PB. And it's PB solid. All right, now the sheet of paper I gave you, let's take a swipe at this way and fill this out, because I probably will have you turn this in with your homework, this sheet of paper. Yeah. So turn it over to the blank side right now. And here's where we want to start. This is what did not print. Okay, so I said, so take that and replace solid platinum with solid lead. Use these half reactions. And this kind of coincides. Remember early on in one of the lectures on chapter 8, I gave you the half reactions for a lead storage battery. I'm not sure I gave you E0 values for it, but it said basically what you have is lead oxide being, so that's a lead plus 4 being reduced to a lead plus 2. It's taking 2, so the top one is reduction. And it's taking 2 electrons to reduce the lead plus 4 to lead plus 2. And it has an E0 of positive 1.685 volts. Sorry, I didn't put the units after it. Volts.
Should we be writing out this problem?
I think so. Yes.
Do you want everything or just the equations?
The
answer.
So here on A, then, I want you to write an overall reaction based on those 2 half reactions. And then the standard E, the E0 for that is going to be the sum of those E0. So it's pretty straightforward. Try to find I got too many papers. Find my calculations. And here we go.
Did you say we needed to leave this as HSO4 aqueous, or can we make H2SO4?
Well, I would leave it as 4H plus SO4 minus 2. Okay. Not exactly sure why I'm saying that, but I would leave it that way.
You said in the email like we were using it to calculate delta G, and there wasn't delta G values for
H2SO4, yeah. Right? And there are. We've since found some.
Okay.
But there aren't in our book. They weren't. I couldn't readily put my fingers on them. We finally did find a little bit. I think sulfuric acid is a little funny. It associates with HSO4 minus. Doesn't give real clear numbers. Okay, part B. You got that? Oh, let's just write that out. So we're going to have a lead solid. I'm not going to put the subscripts for right now, but they're up above. A lead oxide, 4H plus, 2SO4 minus 2 is going to produce 2 lead sulfates and 2 waters. Is that all we produce? Yeah. And we have 2 electrons in the reduction and 2 electrons in the oxidation. So N equals 2. E naught is just the sum of this. All right, and that's the answer that's given. Okay? All right, now part B, you should have already solved this for the minus 25C scenario.
Yeah.
And let's compare our answers there. So look at your homework. E equals,
1.917.
okay. I had 1.9166425.
Yeah.
That's what Tasha had. All right. Okay. 1.917 volts. All right. So I don't know what approach you took, but you can take this approach. What equation could you use to get your delta G?
Negative NF epsilon thing.
E naught. Okay. And N, like we said here, is 2 electrons. All right, and you get something like, all right, so now,
But is that E naught? It's still E naught even though we're at a different temperature, right? We talked about this, didn't we? That E that we just calculated is still E naught even though we're at a different
oh,
temperature?
wait a minute. No, I guess we would be calculating,
Because we'd be calculating delta G, we'd be calculating
Right.
delta G naught. Delta G naught would be at
That.
25C or whatever.
right,
Yeah, but this is...
Right.
So, okay, I see what you're saying, yeah.
yeah. So we're going to do the delta G of this reaction. What is this reaction? It's occurring at minus 25 centigrade. Yes.
Do you want us to be copying down all this stuff too, or if this is what we did in the homework?
I guess if you got this in the homework, just put that down. And
Okay.
Just put did it in the homework.
yeah, it just says did it in the homework. Right. Right. I just want to see the approach you took. All right, so that's for delta G. So what did you do next? Delta H or delta S?
I did delta S.
I did delta S.
I did delta H next.
Doesn't matter.
Probably third.
Well, it might matter because
Yes, because of
if some of you did delta S next, then you might have done your delta H by delta G equals delta H minus T delta S.
I tried doing that first and it didn't work at all, so then I went back and did it.
Yeah, that would be working off of enthalpy, standard enthalpies,
Yeah,
and we're
it
at
was probably-
25C. Okay, so how did you do delta S?
Delta S equals NF
D
over T.
Now, that's going to be the change in E naught with respect to T?
The change in E,
Just E.
just E, because that equation that you give, that was given right above.
And you're getting that, how are you getting this?
Derivative of that
E.
equation with respect to T, so...
That equation is E with the variable T up top. But E equals 1.91737 plus 56.1 times 10 to the negative 6T.
Yeah?
We took that, we took the derivative of that.
Took the derivative of that.
With respect to T, yeah.
Okay.
And we got 56.1 times 10 to the negative 6 plus 2 times, yeah, so then it's 2 times 108 times 10 to the negative 8 to times T. It's like,
.000.
yeah, you could also,
Yeah, I don't know why they gave this 108 times 10 to the minus 8th. It's not up here, but it's here.
yeah.
You know, I mean, you're in scientific notation.
Just said
1.08 times 10 to the minus
yeah.
6th or something.
Yeah.
Okay. Okay, so, and what did you get? What is the change in E with respect to T?
When t equals negative 25, the derivative equals 2.1 times 10 to the negative 6.
And that is like volts per degree K, right? Yeah.
Oh, yeah.
Okay, so it's really a slight, it's a very slight change in entropy with respect to temperature.
Yep.
Okay. And so what did you get for delta S at minus 25?
0.405 joules per Kelvin.
Okay, so you got the answer. And then delta H, what equation did you use for delta H?
Negative NF
Epsilon plus T D.
times, in parentheses,
Correct.
E minus P dE over dt.
E minus what?
T
Right, plus,
dE over dt.
not plus T.
It's plus. I got plus because I thought the equation in the book was wrong.
The equation in the handout was incorrect.
Or whatever.
Well, wait, we talked about this on Monday, and we
Yeah.
said it was wrong, should be,
I think it was handed out to us positive, and it should be negative.
Oh, I got what was ever on the.
Well, we can see which one gives us the right answer.
It doesn't matter because that number is so small.
it doesn't
Yeah, so like I figured it out and then
Okay.
and it was changed.
Yeah, right. And delta H ends up in the answer is the same as the delta G.
So it should be a minus.
So it's a minus.
Where is that equation in the book?
Yeah, I tried to change that.
Oh, I'm in chapter 6.
That's equation 8.30.
Oh, that might make sense why we got the other one. Oh, no, not that.
Well, the second edition changes that to negative.
Okay. We should probably go with that.
Yeah,
Second distance part, right?
okay. But we're saying we can't tell from the answer because
Because
it's such an
yeah.
inconsequential contribution.
Yep.
And even the example, even the example in the text, example 8.6, has that delta E over T, the delta E with respect to delta T as 8.4 times 10 to the minus fourth volts per K. So it has a minor, okay, so we're fine. So let's go on to, we don't need to belabor this anymore. What did you get for E at plus 35? And this one I didn't do, actually.
1.921 volts.
921?
Yep.
All right. Okay. I did the minus 25. I didn't do the plus 35. So, and so then the same logic to go down through here.
But we got different answers for delta H and delta S than what was in the back.
Okay. All right. I'll take a look at those. And if you want to just, to me, the main important thing here is to just kind of understand this overall reaction. What really are the half reactions here? I don't know what you might, did you write those half reactions based on what was above there?
I didn't find those. Originally, I did find those two half equations in the textbook. I think there's a table of half reactions. I didn't find those, so I wrote something different.
Okay.
I just
And
don't
of
know.
course, we've got H2SO4 up there. So, okay. All right. That's probably enough on number 4. And do we have to go back to 2? Did we cover that well enough?
I have a question.
Yeah, on 4?
Yeah. Delta H. Isn't it important that it is? Oh, never mind. I messed up. Sorry.
All right. Number 2, what did we say there? Now, maybe not all of you heard that. On 2B, don't worry if your answers aren't agreeing with the answers included there. My expectations on 2B was basically what I said right there. Guess at a gamma, recalculate, I forget what equation you'd use there. I guess it's is that the Debye-Huckel?
Mm-hmm.
Calculate an MI, and then see how it compares to the MI you got by the classic method, and then adjust your gamma. Try to figure out what do I need to do to gamma to get closer to the answer. So that's what we mean by an iterative process. Just try it.
So are we always just going to be able to assume on these problems that molarity is the same value?
No, I don't think. Very low, and you asked the question, what do I mean by low? But in low, in very dilute solutions, that's a safe assumption. Okay, if it starts getting up to, I don't know, 0.3 molar, then you could be drifting away from there.
Okay.
Like the one where I have the blood plasma. If you were looking at a solution that was any more than 0.9% sodium chloride, you'd probably start to really need to adjust for the density, because the density is going to change on a 2%, a 4% solution is going to start drifting away from the density of normal water. Okay, so it's not always an appropriate approximation, but in very dilute solutions it is. So on question number 1, where it's actually giving you densities that are a little bit off the density of pure water, like nitric acid, 3.15 molar nitric acid has a density of 1.1026 grams per milliliter. You got to take that into consideration to convert that a molarity to a weight percent or a molality. Okay. All right. Do you want to keep these, or you want to just kind of put your name on it and turn it in with that?
Yeah, we can do that.
Just make sure you get your name on there.
I mean, we can just staple it onto the back of it. I'll staple it on here.
You have a stapler?
Yeah.
Great.
And I only did 2 iterations. 'Cause I
That's
was trying
good.
to solve the problem, but
2 or 3 iterations is fine. I'm not going to look for, whether you got the right answer.
Yeah, I did. I like to restable them, like 2 of them are on top of each other, so okay.
Okay. Everybody got the stapler on there? You got it. Hey, you staple?
Give me my stapler back.
Grant, can you?
Yeah.
A staple?
Liz Ryan stole it.
Why do you always go to assume me? I'm all the way over here.
Sorry, I didn't.
Grant, can you do this? Can you do this?
No. I'm too cool for that.
Great.
Okay, so for about 10-15 minutes, let's get back to chapter 8 and just see. I'm down here to slide 17. I'm not sure how far we got, but I just stopped there to show that this is second edition. That's the first edition. I'm going to just motor through these, and if I see some writing on there, I'm going to assume we covered that slide already. Yeah, this is kind of just the topic of one or two of the first problems on the review sheet. Here's a good one for you. This class has introduced us to a bunch of different mathematical things. We even had one equation here where we had to go from ln to log as we looked at electrochemistry related to the pH meter. We've had enough calculus. We've done, I'm trying to just kind of think of some of the other things, but how do how would you take the fourth root of a number?
You go to the 1/4 power, or your calculator, go to the 1/4 feature. Fourth root feature. Well, it's like an X root.
So if you have one of these, you go to math, you go down here, and then switch this to 4 or 5 or 55 or 555. Or you can just go 1 to the 1.
Everybody with Grant?
Yeah.
Yes.
Have you done to the fourth powers?
I mean, I do. There's this one equation we've been using, heat transfer, that says the 8/27. So
8/27 power?
So it's like, that'd be the 8th, that thing would be 8th power to
Okay.
to 27.
So if you're undoing a fourth power though,
not square root.
like if it's that equals, like this thing on the right equals something, right? Equals a number. How do you solve for
X?
Yeah. Like
You have to do the fourth power.
You just
It's
to the
just
fourth,
like
right?
it's just like the square root.
So
it's just the 1/2
to the
power.
2. Yeah.
So
square
to do
is
that,
square.
Grant,
It's
did
just-
you have to change the mode?
No.
You don't change the mode?
No.
Okay, well, you can show me. I'm going to hand out this worksheet. I found myself trying to solve it iteratively. I had a number, and I said, okay, let me take a guess at that and multiply it. Take it to the fourth power and see if I can get the number.
Yeah.
And I came pretty close in most cases, but took a while. So yeah, you're gonna have to show me how to do it on your calculator. And why?
Do you have
Why do you?
these fancy ones?
Well, I do. But this one is one where my batteries seem to mess with me.
Well, that one is gonna be a little bit different. So on that one, you're gonna go just pick
Yeah,
a
see,
number.
my batteries aren't working right now.
You're gonna have to use
That's
parentheses
the one
on
that
that one.
mentioned you on the exam that didn't work.
Yeah,
you tried to use it for
you see why I loaned it to you so readily.
You can have my broken calculator.
Oh, you wanted one that works. Oh, you should have said so.
Did you not use it up there?
He has another one that's just like basic functions, and I use that one.
I bought all brand new batteries for that. Even the little thing like that I had to go find it. Put it all in there, and
won't
still,
work.
it seems like well, I leave it.
That's over here. I might have an idea why it's broken.
In terms of just setting it in sun mode.
Okay. Are you going into electrical engineering?
No.
Okay. All right. Well, why did I bring this up? Well, you'll see on the worksheet in a minute.
Oh wait, what was log? Sorry, I missed that.
Well, what pH is the negative, the log
Yeah.
of the hydrogen ion concentration,
Yeah.
and we had an equation in there. Don't worry about it. We had an equation where it's getting down to really what is the equation driving an hydrogen ion specific electrode, and you had to convert a log to natural log.
Okay, and that's to the fourth. Or just,
No. It's like you multiply it by E.
oh, okay.
You have to multiply by E to get from log to natural log. Okay, KSPs, we went into that, so that's relevant. Ionic strength. The examples I give today are going to deal with this, or the review worksheet. So ionic strength. And the point here, notice in this example, ionic strength, we have a 0.1 molal sodium chloride, sodium sulfate, calcium phosphate solutions. So we're talking same concentration solutions. But what do you get here? You get 0.1 molal sodium, and you get 0.1 molal chloride. Here you get 0.2 molal sodium and 0.1 molal sulfate, right? And on the calcium you're going to get what are you going to get? 0.3 molal calcium ions and 0.2 molal phosphate. Is that right? Yeah. So they go into the calculations. Here's your calcium phosphate. 3 times that times charge squared. 2 times the molality times the charge squared. So what's the point? Here's your ionic strength of sodium chloride. Here's your ionic strength of the sodium sulfate. Here's your ionic strength of the calcium phosphate.
Oh, so there's 2 phosphates and 2 calciums.
Yeah. I think the assumption that's going into this is that at that concentration, those compounds are going to be completely dissolved. Okay? And that's probably not a safe assumption right here. This is highly insoluble. Calcium phosphate?
Aren't most calcium things pretty soluble?
Yeah, most phosphates, yeah.
Oh, that too.
But, well, a calcium chloride is like probably about 150 parts per million.
So that's not...
So, so that problem is ignoring that or assuming solubility, okay? All right, here's the Debye-Huckel equation. I guess we never really specifically got to it. All right, here's a comment to make. The test may include the Debye-Huckel limiting law, and I think when you talk about Debye-Huckel equation, that's what they're generally referring to. The chapter talks about the Debye-Huckel extended law, that it won't include that. Exam won't deal with that.
We're only doing the limiting law?
Only the limiting. The extended one is equation 8.52, and we won't deal with any problems with that. I think even the author doesn't really either. Awareness that the Debye-Huckel limiting law can be extended, but one of the factors in there is the radius of the ion, the actual radius of the ion. We're never going to get to that level of detail on these things here. So it can be extended, but it takes more things. It has to take more things into consideration. Yeah, and probably we won't go past equation 8.50. there's a concept called equivalent conductance, equation 8.65. We won't deal with that either. All right, so you can ignore
6.5.
Ignore anything past the Debye-Huckel limiting law. I started to make some outline of what to expect. A general comment would be, here they are, comparable, the exam will be comparable to homework problems. Chapter 7, let's just make a couple quick comments about Chapter 7. And so there was Raoult's law. Remember we talked about the mole fraction of the solution and the mole fraction in the solution and how that impacted the partial pressures. And then we talked about what would be the resultant mole fraction in the vapor phase. So those kinds of considerations, we talked about a delta G of mixing. What is the free energy change as a result of mixing? We looked at colligative properties. There was an equation to show how you can calculate a freezing point depression constant from delta H of fusion. Calculations for the osmotic pressure based on molality and things of that nature. So in Chapter 7, there's a bunch of, there's liquid, multi-component systems, solid, liquid, solid in liquid. Probably the one that was emphasized was liquid. Not to ignore the others, but liquid is where you got into the mole fraction in a solution, the mole of two liquids. You mix two liquids together, what's the mole fraction of each liquid, and what's the resultant vapor pressure of those liquids, and the mole fraction of those vapors in the vapor phase, etc. So that's not comprehensive, but it's just a reminder of some of the things we got into. And then Chapter 8 is a little bit more recent, hopefully a little fresher. And so here's this review sheet. You can look this over, front and back.
This is a review sheet that we should work on Friday.
Right.
Okay.
Yeah, you can work on this on Friday.
And then for like those comments on the video, how much do you want us to write exactly? Or is that another sheet?
It is. And you don't have to go beyond this sheet of paper. Nice. All right? You don't need to type it. You could, but you don't need to type it. Just write it out. On one of them, well, on a couple of the questions, you could go out and look at some other source. He mentions doctrine of creation. He doesn't really mention creationism until, oh, look at it, started snowing.
Yeah.
He didn't mention creationism until we got in, I don't think, as I recall, until we got into the Q&A section after his presentation was over. And I don't know whether this recording has the Q&A session recorded as well. Probably does. Probably does. And if it does, it may be an hour long. If it doesn't, its first half hour was actually his presentation. And then he makes a comment about mathematics as a universal language, and it seems to me there may be, he may even mention a reference that talks about that, a book or an article or something like that, or you might want to jump out and just see. It seems to me it's a concept that is developed a lot further in the literature and books and things of that nature. All right, so that's all you got to do. Send me any questions you have.
Is the exam 5 questions again? Was like
Probably will be like 7, and you choose 5. I don't have it completely made up yet, but it seems to me that was a proper length of an exam. You were all able to do those problems in an hour and 20 minutes or so. So I try to get in that realm again. Yeah, I think you'll do fine.
Can we go back to the limiting law and like talk about it in words a little bit? Like, what is it limiting? I'm a little confused on it, like conceptually. Like, I can plug in the numbers.
I forget where.
It's towards the end.
So, it comes after ionic strength. Okay. Yeah, so you have to introduce the ionic strength, because actually the limiting law, ionic strength, is a part of it.
So would you say that gamma is limiting the ionic strength of like potential solution? Or is that?
Well, I think what the author is pointing out is that, and I'm not quite sure I get it. He's saying one of the benefits of this is you get into something that is kind of independent of what the ions are. Just what is this ionic strength? But it seems to me to get to the ionic strength, the identity of the ions plays into that.
Yeah. Which is gamma, right? So gamma would represent like that is dependent on the ion that you're using. Is that?
Yeah. Right.
If you have that gamma times molal equals activity or something. So that gamma is dependent on the ion.
Yeah, there's I think I have it on a slide here. Here we go.
Okay.
Here's a table of gammas. And so here's a table of gammas, irrespective of what the ion is. This doesn't.
Doesn't matter just.
It doesn't matter whether it's a sodium. So the +1 charge. Doesn't matter whether it's a sodium, potassium, cesium, whatever it is. It's just this charge at these. At various ionic strengths, you can get a gamma.
What are the 9, 7, 5, 3? Activity coefficients by charge. Oh, I think those are the activity coefficients. 9, 7.
That's the amount of charged ions, I think.
Is it?
But how can you have an odd number of charged ions?
4, 5, 6, 4, 6, 8, 3, 5, 7, 9. What do we got here? Angstrom. plus or minus
I
charge.
guess it's probably the size of the ion. So you look at
Oh,
the
yeah.
charge of the ion, then you look at the size of the ion.
Is that like
and you go over
angstroms?
to the
Yeah, okay.
Yeah,
ionic strength
10
and
to
find
the-
activity coefficient from
It's
that.
that parentheses there. That parentheses right above it is, I think, standing for like
Yeah, because it's an
the number of angstroms. Yeah.
Okay, so actually on your review sheet, on the back, if you look at 5C, okay, 5C, I want you, after you calculate a few things on number 5, I want you to come back to 5C and hunt for the appropriate gamma plus minus values based on the mean ionic strength, based on the ionic strength that you calculate for this reaction I'm giving you in 5, is then come down to this table and find the appropriate gamma. Now,
So we need to know the angstrom size then.
yeah,
Of that of
I didn't
nitrite.
quite
nitrate.
take that into consideration. So
Well,
what
it
what
doesn't
is
change
this?
that much, to be honest. There's
So
a lot of
it's
them.
Yeah.
independent of ion, but not independent of ion size. Like you don't need to actually know the ion. You just need to know the
Yeah.
size of the ion, right?
So
And the
why don't you go, let's see, what do we got? We got a plus,
Yeah.
we got a -1 and a +3. And I went with these top values,
Okay.
okay?
Go with those.
Without knowing the ionic size. So, yeah, I think you're gonna come up with these values. Because you got a +3 and a -1 ion in your calculation.
But on the test, if we had to do something like that, we would be given the ionic size.
Yeah. Or a limited table.
Yeah.
All right? Any other questions? You probably want me to run off and grade your homework.
Looks like a lot, just basically only electrochemistry. This-
Yeah. That skips chapter 7.
But chapter 7 still on test. Okay.
Yep, chapter 7 and 8.
We're skipping the chapter.
Will you email out answers to this review sheet Sunday night?
Sunday. What about like Friday? Since we're probably gonna work on this on Friday.
I'll try. I think I did most of this. 1 and 2 we did right on the slides in class. We just derived those equations. That's pretty straightforward. Number 3. Number 4 is just like that example I just showed you, calculating the ionic strength. Just have to work off of the formula for magnesium phosphate. I'll try to do that. All right? And email me if you have any questions, and I'll see you Monday,
Thank you.
12:45 or 12:30ish.
You said that's not open book?
Yeah, not open book.
Yeah, I think something's wrong with your calculator itself. Did it ever turn on?
Yeah, I used it for a long time. And then all the batteries died, so I put new batteries in it. I don't know, maybe I should just try some new batteries here. That's a fairly new battery.
Well, that one's just like the backup once those other batteries are dead.
This is?
Yeah. It's like a backup. Just,
Oh, so that's when it says batteries are getting low?
yeah, probably is when your batteries die now. It's just
Really?
or something like that. Four-day weekend? Oh, you have a 4-day weekend?
Yeah, it is snowing. So those weathermen or women kind of knew what they were talking about?